Let us now formally define probability. So let S be a finite sample space of a probabilistic experiment. Suppose each outcome is equally likely. Let E be an event in S. Then the probability of occurrence E, written in this way, is given by the probability of E, that's how we read that, probability of E is equal to the cardinality of set E over the cardinality of the sample space S. So it's the cardinality of event E over the cardinality of sample space S. Now, the likelihood of any outcome in a sample space is given by that probability function. It is described as a function, that's why it's written like this, that assigns to each outcome a real number. So this will come out as a real number, and that's what we call the probability of that specific outcome. So these real numbers are in between 0 and 1. Most of the time, there are fractions, decimals, or percentages. Even though they are not discrete in nature, because when we say discrete numbers, they should be whole, or at least whole numbers, or at least integers, the probability that we're counting of is the discrete one. We're looking at discrete sample spaces. That's why this is still considered under discrete data or discrete numbers. So let's have this example. Consider the experiment of throwing a fair die. Let event E be the number on top face is an even number, and the number on the top face is an odd number. We are asked to find the probability of event E and the probability of event F. So first, let's look at the sample space of throwing a fair die. When we throw a fair die, it has the possible outcomes 1, 2, 3, 4, 5, and 6. So, event E is the number on the top face is an even number. So that would mean, let's get all the even numbers, 2, 4, 6. So this is the elements of event E. Event F, the number on top is an odd number. So for F, I'll just get me 1, 3, 5. So the probability of E now would be the cardinality of set E, which is actually 3, over the cardinality of the sample space, which is 6. So the probability that the number on the top face is an even number is 3/6, or rounded off 1/2. Presented in decimal, it's 0.5. In percentage, it's 50%. So it depends now on how you'll be able to easily understand that the probability that the number on the top face when you throw a fair die is an even number is a half, 0.5, or 50%. So if we're going to do the same thing here for event F, the probability of F would then be the cardinality of set F, which is actually 3, over the cardinality of the sample space, which is 6. So this is written in lowest terms as 1/2, in decimal as 0.5, in percent as 50% as well. So this meant that the probability of getting an even number on the top face when you throw a fair die is half, 50%, and the probability of getting an odd number is half as well, 50%. Now, if you're going to take notice, these two events cannot happen at the same time. As you can see, there are no common elements, which would mean that I cannot roll a die and get both an odd number and an even number. Such events are what we call mutually exclusive events. So events A and B are said to be mutually exclusive if they cannot occur at the same time when the experiment is performed. In terms of set, this means that A and B are disjoint. That would mean A intersection B is a null set. We also call A and B an impossible event. So, writing here what we had a while ago, given the sample space of throwing a fair die, 4, 5, 6, event E, it's all the even, so that's 2, 4, 6, and event F, That's 1, 3, 5. As we can see, if we are going to get this intersection, E intersection F is actually a null set. Oops, let's write that more properly. A null set. There you go, because there's no common element. And since there's no common element, we say that these two events are mutually exclusive. They cannot occur at the same time. So, let's have another example. In a deck of playing cards, exactly one card will be obtained. When we talk of playing cards, it is our standard deck. Standard deck of 52 cards, 4 suits, 2 colors, 13 characters, ace to 10, jack, queen, and king. So, those are our playing cards. Our experiment is let exactly one card will be obtained. We are given with the following events. The card selected is a heart. The card selected is a face card. It's an ace, an 8, a 10, or a jack. Oops, that is typographical. That should be I here. So the question is, which of the following events are mutually exclusive? Pause the video and try to see if you'll be able to differentiate which events are mutually exclusive, which ones are not. Alright, so let's first look at A and B. A card is a heart, and the card selected is a face card. We know that we have Jack of Hearts, Queen of Hearts, and King of Hearts. These are the face cards, Jack, Queen, and King. And there is a heart, a Jack of Hearts, Queen of Hearts, and King of Hearts. Since they can occur at the same time, we can have a heart and a face card. So A and B are not mutually exclusive. Mutually exclusive. How about A and C? A heart and an ace. We know that there's an ace of hearts, so this can occur at the same time. So A and C are not mutually exclusive as well. How about B and C? A face card and an ace. We know that the face card is only Jack, Queen, and King. It cannot be an ace. So therefore, events B and C are example of mutually exclusive events. How about B, C, and D? Do we have a face card that is an ace and is also an 8? It is impossible that we can get a face card which is ace and also 8. So B, C, and D are also mutually exclusive events. B, C, D, and E. We already know B, C, and D are mutually exclusive. However, E, the card selected is a 10 or a jack, but a jack is a face card. So B and E have common elements. B and E are not mutually exclusive. However, we're asking for all of them. So we cannot say that if two are not mutually exclusive, then the rest are still mutually exclusive. So here, this is not mutually exclusive because again, B and E are not mutually exclusive.